Good evening. Good afternoon. Good evening. No, it's good. It is evening now, isn't it? What time zone am I in? This talk is Project Jigsaw Under the Hood. My name is Mark Reinhold. I work on Java. Hi. And I am at the wrong end of this deck. Excuse me. All right. It's always disturbing when it says end of show on your first slide. So, quick show of hands. I'm just curious. Has anybody tried the JDK 9 early access builds? Oh, excellent. Very good. Has anybody tried the JDK 9 with Jigsaw early access builds? Excellent. Okay. Who attended Prepare for JDK 9 yesterday? Who attended Intro to Modular Development? Who attended Advanced Modular Development? All right, we're ready to rock and roll. We're going to do some module science. We're going to science the out of modules. Okay, first I'd like to do a quick review of the modularity landscape because there are kind of lots of moving parts here. First, the Java Platform Module System is being defined in the JCP for Java SE9. The expert group for that started its discussions back in February of this year. Second, the Java SE9 platform itself will be defined in the JCP, although that particular JSR has not yet been filed. This JSR will own the modularization of the Java SE API, that is the allocation of Java SE packages like java.lang and java.sql into specific modules. Third, Project Jigsaw is an OpenJDK project to implement the Java Platform Module System. That's JEP 261. It includes support for modules in Java-C, Java-Doc, and the Java Launcher, and so forth. Project Jigsaw also splits the JDK into modules. Remember, the JDK is the reference implementation of the Java SE platform specification. There are 3 JEPs for that, 200, 201, and 260. These modules will be an input to the Java SE9 platform JSR when it modularizes the Java SE API. Project Jigsaw also replaces rt.jar and tools.jar with new runtime image and directory layout. That's JEP 220. This will help modularity in the long term, but it's not directly related to the module system. It's an implementation change specific to the JDK. With all these JSRs and JEPs, you might be wondering what this talk is about. When you use JDK 9 and the features implemented in Project Jigsaw, you're subject to the rules of the Java Platform Module System. That's what's under the hood, so to speak. So really, this talk is about the Java Platform Module System. This talk has 3 parts. The first part explains how the module system works with the language and virtual machine to offer certain guarantees. The second part is about migrating to modules. The third part is really under the hood, what the module system is fundamentally capable of beyond what you can express in the Java programming language. I'd like to set some expectations for this talk. The style is quite different than the style of a talk about, say, lambdas. Lambdas are about the shape of programs in the small, individual for loops turning into method calls with lambda arguments and then growing into something that uses streams, perhaps. You can reshape a program to use lambdas without anyone noticing. Modules are about the shape of programs in the large. We deal with classes and packages and get bigger from there. If you reshape a module, it's quite likely that other people will notice. So this talk is less about the code you can write than the kind of systems you can set up. Also, because modules affect all phases of development, compiling, testing, packaging, deploying, and running, they're much more connected to the tools ecosystem than a feature like lambdas, which really only needs IDE support. Tools like Maven, Gradle, and Ivy don't support modules yet, but that's okay. The JSR is still in progress. Everything will be all right in the end. So if it's not all right, it's not yet the end. Part 1, accessibility and readability. Everyone knows the hierarchy of accessibility in the Java language and virtual machine. It's simple to understand, easy to use, well, maybe not the protected part, and strongly enforced by the compiler in VM. However, it has a big weakness. The only way to share code between packages is with public, but then you're sharing with everyone. It's not surprising, therefore, that package friendship in one form or another has been requested many times over the years. One goal of the module system is strong encapsulation, to allow a component to declare which of its public types are accessible to other components and which are not. The lines in italic are the levels of accessibility connected with the module system. Reading upwards from the bottom, you can arrange for types to be accessible only within their module, or accessible within their module and to other specific modules, or accessible to all modules. As usual, migration drives a lot of our thinking. We want to make it easy to place an existing package into a module and immediately give that package the benefit of strong encapsulation. We don't want each and every public type in a package to have to opt in to strong encapsulation, so public types in a package are not accessible outside the module by default. That is, public on a type declaration no longer means that everyone can access the type. This is a fairly big change. Now, what happens if someone tries to access a public type that's not accessible? Here's an example from Glassfish. It doesn't start on JDK 9 because the VM throws an illegal access error. The error message is, that's rather small, class com.sun.enterprise.security.provider.policy wrapper in module unnamed module cannot access class sun.security.provider.policy file in module java.base. Don't worry about what an unnamed module means yet, we'll get to that. The point is that the policy file class is declared public, but since it's a JDK internal API, it is now accessible only within the java.base module. Sorry, Glassfish, but you need to find an alternative to this internal API. In Java SE9, modules are first-class program components, like classes and interfaces. Here's the declaration of the java.sql module that contains JDBC. It's in a file it's in a file named module-info.java in a directory named after the module. The compiler treats it like any other Java file and translates it into a module-info.class file, which you can put in a jar file in the normal way. We call the result a modular jar. The package hierarchy exists in the same directory, source/java.sql, so the module declaration is outside of all the packages in the module. It's the job of the module declaration to say whether a package is strongly encapsulated or not. It's really easy to get strong encapsulation, just don't mention the package in the module declaration. To allow other modules to access the package, or more specifically to access the public types of the package, add an exports clause. You can export to all other modules, or you can say exports to a specific module or list of modules to give access only to your friends. At compile time, Java-C prevents code outside of the java.sql module from accessing types in any packages except for those listed. You get the same compile time error as when you try to access a package private type from outside its package in Java 8. At runtime, the VM throws an illegal access error, like you saw with Glassfish. Let's dive into the VM more deeply. Traditionally, accessibility in the Java platform is about who is doing the access and what is the public protected private flag on the target class. At runtime, the VM uses the class loader of the accessing class to find and load the target class, and then the VM checks the flag on the target class. Because the VM relies on class loaders, people can create loaders that only know how to find and load classes of certain packages. Loaders can, in a way, isolate one package from another. Now, in the top picture here, the class p.c is trying to access class q.d. The loader for p.c knows to delegate to another loader for any class in package q, such as q.d. Only when that other loader has loaded q.d can the VM check its flags to determine if p.c can access it. In the bottom picture, the loader for p.c has no idea where to find package q, so no access to q.d is possible from p.c. Technically, this is not a failure of accessibility. because the VM never gets to check the access flags of q.d. Instead, it's a failure of visibility. q.d is invisible to p.c. Still, the effect is quite powerful. If the class loader of the accessing class cannot find and load the target class, then it doesn't matter if the target class is public. It's effectively encapsulated. Whoever sets up the class loader sets up the encapsulation. Encapsulation based on class loaders, however, is not strong encapsulation. It relies on packages being carefully apportioned into different loaders, but that isn't how the JDK works. Most code in the JDK is loaded by the bootstrap loader, while code on the class path is loaded by the application loader. Spinning up lots of loaders for all this code would be a compatibility nightmare. In any case, there's no actual isolation anyway. You can circumvent class loaders by getting hold of references to Java-lang class objects. Once you have a class object, class loaders are irrelevant, and it's impossible to stop references to class objects from being passed around. Strong encapsulation is about being able to prevent access even if the accessing class and the target class are in the same class loader, and even if someone is using query reflection to manipulate class objects. Let's assume that different modules are somehow mapped to the same class loader. Can class p.c in module X access class q.d in module Y? Another goal of the module system is reliable configuration, to replace the brittle error-prone class path mechanism with a means for program components to declare explicit dependencies upon one another. So in order for p.c to access q.d, not only does module Y need to export package q, but module X needs explicitly to depend on module Y. The formal name for depends on is readability. Readability underpins accessibility in the Java language and virtual machine. The accessing class, p.c, must be in a module that reads the module of the target class, y, and the module containing the target class, y, must export its package q to at least the module of the accessing class, x. You can see that accessibility is a two-way street. X reads Y, and Y exports package Q to X, and probably to many others. Note that accessibility is independent of class loaders, just like before the module system. This is important for two reasons. First, it means accessibility works at compile time, where there aren't any class loaders. Second, it means you can reason about accessibility based only on requires and exports clauses in module declarations. There's no need to worry about the class loaders that might or might not be in existence at runtime. In fact, accessibility is pretty straightforward. A package is either exported or it isn't. But on readability, there is more to say. When you depend on a module, you depend on a hopefully coherent collection of packages that it exports. In some sense, those packages are the interface of the module. Inside the module, hundreds more packages may sit encapsulated, waiting to help implement the interface. More than that, when you depend on a module, you implicitly depend on all the modules it depends on. For example, if you depend on the java.activation module with its 35 classes, then you also depend on the java.desktop module with its 5,583 classes. If the watchword for JDK 8 was functional, then for JDK 9 it's transitive. You should think in terms of the transitive set of modules needed by your application. The indirect dependencies can also be as important as the direct dependencies. Let's see how readability handles this. I'll use an example of readability from the graph of Java SE modules. The java.sql module that holds JDBC requires the java.logging module that exports the package java.util.logging, everyone's favorite logging API. This lets code in the java.sql module access the public types of Java util logging, such as logger. You can see that some code in the JDBC driver manager class is newing an instance of logger. What if the API of the java.sql module, rather than the implementation, wants to use the logger type? For example, the JDBC driver interface has this method getParentLogger in it that returns a logger. Let's look at this through the eyes of an application module that uses JDBC called MyApp. In order to use the driver method that returns a logger, the MyApp module not only needs to read the java.sql module, but also the java.logging module, which exports the logger interface. It would be a pain if the developer of MyApp had to remember to say requires java.logging when using the API of java.sql. Well, there's good news. The java.sql module can take on the responsibility of remembering this for all of its clients. Look at the java.sql module now. It says requires public java.logging. The word public here means that any module that reads the java.sql module also reads the java.logging module for free. No extra work required. The MyApp module doesn't have to bother with requires java.logging because it reads java.logging thanks to java.sql. This is called implied readability, and it's very powerful. It's powerful because it lets a module be refactored without breaking its consumers. For example, suppose that JDBC has a java.sql.time package that we'd like to ship as a separate module. This new module is at the bottom right. The java.sql module can say requires public java.sql.time so that MyApp, which explicitly reads java.sql, implicitly reads java.sql.time. It goes further. We could refactor the java.sql.time module by extracting a java.sql.date module. The java.sql.time module would say requires public java.sql.date so that anyone who reads java.sql.time also reads java.sql.date for free. The MyApp module would be completely unaware that any of this is happening. In essence, the readability model supports downward decomposition. Any module you read can be decomposed into new modules, and readability of the new modules can be recovered with a requires public clause in the old module. You can see that the definition of reads is actually recursive. A module X reads another module Y by requiring it directly, or by reading some third module Q, there's the recursion, where Q says requires public Y. And now that X reads Y, Y can say requires public Z, and X will then read Z. Now be careful. Once people require your module explicitly, you can refactor it as much as you like, but you cannot delete it. There's no way for a module to stand in for another module by taking its name as an alias. If someone requires X and X is deleted, then the module system will not start. Core reflection. Everything so far has been about accessibility in the Java language and virtual machine, where the accessing class p.c and the target class q.d were known statically. Accessibility extends to dynamic class references that you manipulate with the core reflection API, that is java.lang.reflect. In this example, C is a reference to some class object. The reference is dynamic. We can't control which object is referred to by C at runtime. Maybe it's a class object that represents a private class of an unexported package of an unreadable module. That is a class object representing an inaccessible class. Similarly, we cannot control what MS refers to. It might be some of the private methods of some inaccessible class. However, we want to preserve strong encapsulation even when core reflection is used to access types and their members. The only opportunity to do this is when an operation is performed on a Java lang reflect method or a Java lang reflect field. Operations such as invoke and get and set on these classes perform the same pair of checks, the same two things that the compiler does and the VM do. Does the caller read the target module, and does the target module export the relevant package to the caller module? Even setAccessible respects strong encapsulation. Suppose you have a Java lang reflect field that represents a private field of a public class, but the class is in a package that's not exported by its module. SetAccessible true will fail. It can't manipulate the accessibility of anything in a non-exported package. Just like the get and set methods on a Java lang reflect field, setAccessible performs the same pair of checks as the compiler in VM. Does the caller module read the target module, and does the target module export the relevant package to the caller module? If that all checks out, then the private field can be made accessible via setAccessible_true. An advanced topic in core reflection is proxies. Java-Lang Reflect Proxy is a miniature framework that offers a way to get an object whose class implements various interfaces. The class's methods delegate to an invocation handler that you supply. The class itself is meant to be secret, an implementation detail of the proxy class. In JDK 9, the proxy class strongly encapsulates the secret class by declaring it in an unexported package of a freshly created module. This means the proxy object must be invoked through interfaces, which is as it should be. The proxy class can even cope with some of the interfaces being in unexported packages. Behind the scenes, the proxy class tweaks the module declarations to export the interface's packages to the fresh module. So that's accessibility and readability. To summarize, accessibility used to be a simple check for public or same package. In Java SE 9, accessibility strongly encapsulates module internals. Accessibility relies upon readability, which can be direct or implied, and accessibility is enforced by the compiler, the virtual machine, and core reflection. Part 2, different kinds of modules. Everything so far has been about named modules, modules explicitly declared with a name in a moduleInfo.java file. What about jar files on the class path that don't have a moduleInfo.class file? They seem to be in some weird world of their own. To keep the model of accessibility and readability consistent, we've introduced the concept of the unnamed module. All classes not in named modules are implicitly in the unnamed module. It's as if everything on the class path is in one big special module. Because it's a module, we can ask the two usual questions. What does it read and what does it export? What it reads is very simple. Every named module. All of them. As if by magic. For free. This means anything exported by a named module can be accessed by the unnamed module. You can turn a jar file into a named module by adding moduleInfo.class to it, put the jar on the module path where modules are found, and the jars left on your class path will not realize that anything happened. That's a huge help for migration. The next question is about what the unnamed module exports. Before that, though, we should ask, who reads the unnamed module? Remember, a goal of the module system is reliable configuration. We believe very strongly that named modules should not read the unnamed module out of the box. It would make a mockery of reliable configuration to make modules depend on the arbitrary content of the class path. So you can't write requires unnamed or requires class path or something like that in a module declaration. There are no reads edges going out to the unnamed module. Of course, this is a huge hindrance for migration because any jar you turn into a module cannot access the jars that are left on the class path in the unnamed module. The answer is the concept of automatic modules. You can take a jar, say guava.jar, and move it from the class path to the module path. This turns the jar into an automatic module. That's all you have to do. You don't need to change the jar in any way. An automatic module is a named module declared implicitly rather than explicitly. Its name is derived from the jar file name in an obvious way. Placing guava.jar in the module path gives us an automatic module called guava. As before, whenever you see a module, you should ask, what does it read? What does it export? The automatic module guava reads everything in the JDK image and the unnamed module. It's as if it says requires unnamed. Now the hindrance to migration is gone. You can turn a jar into an automatic module, and it can still access the jars that are left on the class path. We asked earlier what the unnamed module exports. The answer is all of its packages. In junit.jar and glassfish.jar and hibernate.jar, precisely to help the code in the automatic modules which read the unnamed module. Because an automatic module is a real named module, another named module can require it. The JavaFX core module says requires guava, so there is a reads edge from it to the guava module. What does an automatic module like Guava export? That's easy, all of its packages. So javafx.core can access all of the public Guava types. JavaFX.core could even say requires public Guava to transmit its dependency on Guava up to its own consumers so that anyone who reads JavaFX.core will also read Guava for free. So by moving a jar from the class path to the module path, you get an automatic module that lets you start building your own graph of named modules. It is not necessary to wait for every jar on the class path to be modularized by all their different maintainers before you start developing modules that require them. By the way, what happens with a second automatic module, Hibernate? Automatic modules read each other, and all modules in the JDK image and the unnamed module. So Guava reads Hibernate, and Hibernate reads Guava, and they both read all the modules in the JDK image and the unnamed module. In some sense, they read as much as they did when they were mere jar files on the class path. Again, the goal is for you to take groups of jar files from the class path, move them to the module path, require them from your own modules, and have everything just work. So, there are three kinds of modules. We have explicit named modules, such as java.sql, automatic named modules, such as Guava in this example, the unnamed module, also known as the class path, and we get lots of readability for free to help with migration. Part 3, loaders and layers. I said before that strong encapsulation is independent of class loaders. There are no changes in the java.lang.classLoader API due to the module system. Class loading does not change. In some sense, the module system exists underneath the VM's class loading architecture, not on top of it. The module system works with whatever loaders already exist. It doesn't create its own weird and wonderful set of loaders. So JDK 9 has the same 3 built-in loaders as JDK 8, the Bootstrap extension and application loaders. Some implementation details of these loaders have changed, but that shouldn't matter to most programs. Most modules that you've seen, like java.base and java.sql and java.logging, have their classes defined by the Bootstrap loader. A few modules, like java.corba, have their classes defined by the extension loader. A handful of modules related to tools have their classes defined by the application loader. It's important for security that Java SE modules be moved out of the Bootstrap loader if possible. Modules in the Bootstrap loader run with all permissions, which is not ideal from a security perspective. They can only be deprivileged, that is, run with fewer permissions, if they're not in the Bootstrap loader. We've spent a lot of time and effort on moving modules out of the Bootstrap loader so they can be deprivileged. Frankly, for a module as big as java.corba, 1,833 classes and 31 exported packages, that's no small accomplishment. The deprivileging work itself will continue throughout JDK 9 and JDK 10. While the module system doesn't create loaders itself, it is responsible for associating loaders with modules. To help manage this, the module system introduces the concept of layers. A layer is a family of class loaders that together serve to load classes for a graph of modules. Out of the box, JDK 9 defines the boot layer, consisting of the 3 familiar loaders. It's the boot layer that associates the java.base and java.sql and java.logging modules with the Bootstrap loader, java.corba with the extension loader, and so forth. The boot layer is the only layer that most people will ever have to think about, or indeed not think about. But there's a lot more to say about layers. A layer is created from 2 things, a graph of modules and a function that maps modules to loaders. Here's the graph from resolving the jdk.jlink module, which contains the jlink tool for building runtime JDK images. And here's a Lambda expression mapping modules to the Bootstrap loader and the application loader. Creating a layer informs the module system about the classes that will exist in the program and the modules they'll come from. The module system passes this information to the VM so that when classes are eventually loaded, the VM knows which module a class belongs to and what that module reads and exports. It's like the VM has a shadow copy of the module graph that it uses when checking accessibility between classes. Because of fundamental constraints on how class loading works, the module system must enforce certain constraints both on the module graph and on the mapping from modules to loaders. Let's talk about the graph first. This is the graph of Java SE modules. What do you notice about it? Anybody?
No loops.
No loops. Exactly. There are no cycles in this graph. This is fundamental to the Java Platform module system. Cycles would bring an entirely new dimension of complexity. It's taken over half a decade to detangle the tens of thousands of classes in the JDK to the acyclic and relatively sane state you see here. We do not wish that pain upon anyone else. Java Application Architecture is the best book about modularity that I have ever read. In a section titled Cyclic Dependencies, the Death Knell, it says, excessive dependencies are bad, but cyclic dependencies are especially bad. The book goes on to say, generally speaking, cycles are always bad. However, some cycles are worse than others. Cycles among classes are tolerable, assuming they don't cause cycles among the packages or modules containing them. Cycles among packages may also be tolerable, assuming they don't cause cycles among the modules containing them. Module relationships must never be cyclic. So that's clear enough. Let's turn to another requirement on module graphs. A module may read at most one module that exports a package called P. If a module could read more than one module that exports P, in which module would P be accessed? There's no answer. The system is just broken. So we defend against this. Only module graphs which obey this constraint and have no cycles can be turned into a layer. Let's turn to constraints on the mapping from modules to loaders. Remember, the mapping is an essential part of a layer along with the module graph. There's only one constraint. It's due to a fundamental limit on class loading. A class loader can only create one class called C. If multiple modules in the graph have a class called C, then those modules must be mapped to different loaders. More broadly, we say that if multiple modules have the same package, then whether or not they export it, those modules must be mapped to different loaders. There's a secondary constraint that's not practical to check because it concerns how loaders behave at runtime. It's that the loaders must delegate to each other in accordance with the read edges of the module graph. That is, loader delegation must respect module readability. The reason is obvious. If module X reads module Y, then in order for X's classes in one loader to access Y's classes in another loader, X's loader must delegate to Y's loader. There are no reads cycles in the module graph, so you might expect there would never be delegation cycles between loaders, regardless of how modules are mapped to loaders. Unfortunately, this is not the case. You can get delegation cycles if the map from modules to loaders is bad. I'll illustrate this with an example from the JDK itself. In JDK 8, the four org.w3c.dom packages you see here were present in rt.jar and defined by the application class loader. However, it turned out that JAX-P, the JCP standard which includes W3C technologies, never actually included these four packages. Their presence in the JDK was unofficial. What should we do with them in JDK 9? It turns out that JAX-P doesn't want to include them, so the obvious answer is delete them. However, there are lots of XML libraries outside the JDK which assume these packages are always present in the application class loader. Rather than make every library ship its own copy, we decided to ship them in their own module called jdk.xml.dom. This is a JDK-specific module, not an SE standard module. You get this module if you require it explicitly. In the JDK module graph, there's jdk.xml.dom near the bottom. In the boot layer, we planned to map the jdk.xml.dom module to the extension loader, since it has no need to be in the Bootstrap loader. This looks good. jdk.xml.dom requires java.xml, and the extension loader will delegate to the Bootstrap loader for types exported by the java.xml module. Great. Unfortunately, someone added a jdk.plugin module that required jdk.xml.dom, and they mapped the jdk.plugin module to the Bootstrap loader. Oops. There's no cycle in the reads edges, but for class loading to work, there would have to be a cycle in the delegation edges. That's bad. Sooner or later, a delegation cycle would become an infinite loop. But set that aside and consider this. The Bootstrap loader never delegates. So in fact, this mapping of modules to loaders is just wrong, given the reads edge from jdk.plugin to jdk.xml.dom. Fortunately, we caught this in time. One possible fix was to rewrite jdk.plugin to not depend on these DOM packages, so the reads edge from jdk.xml.dom would go away. This fix might sound unlikely, but it's surprisingly common to clean up parts of the JDK and discover that you can cut many such dependencies. Another possible fix was to move jdk.xml.dom up to the Bootstrap loader. Well, that's not great. The solution we actually chose was to move jdk.plugin down to the extension loader. It's not trivial, but it's the right answer for the long term. So, going back to loaders respecting readability, there should be no delegation cycles between loaders, just as there are no read cycles in the module graph. Another aspect of loaders respecting readability concerns split packages. Who knows about split packages? Okay, so you've experienced the pain. A split package is when multiple loaders define classes for the same package. Sorry, a little UI trouble here. Remember that a module can read at most one other module that exports P. That's baked into the definition of a well-formed module graph. If X reads Y, which exports P, then X cannot also read Z, which exports P. If the loaders respect readability, then the loader for module X will delegate to exactly one loader for types of P. This means no split packages, which is a very good thing. Unfortunately, there are libraries out there which include types from packages belonging to java.sc. This means a split package, which traditionally leads to class cast exceptions. If a library like this becomes a named module, then the module system would detect that the module exports the same package as a java.sc module. The module graph would not be well formed, and the boot layer would not be created. Sorry. Oh, great, updates available. That's not what I wanted. There we go. But if the library is in the unnamed module, then the module system doesn't detect the split package. This is because we don't scan every jar on the class path at startup. The results in this case can be rather surprising, so I'd like to present two scenarios to you. One scenario is a jar file on the class path that contains non-standard types in the java.annotation package. In JDK 9, these types will be ignored because the Java SE module graph already has a module that exports the javax.annotation package. Any code on the class path which relies on non-standard types will get a no-class.def found error because Java SE doesn't have them. This error sounds bad, but it means we avoid a split package as soon as it would become dangerous. It's much better than the program running with two distinct versions of javax.annotation because that can generate errors at almost any point in the program's lifetime, and these kinds of errors are famously hard to diagnose. Let's go through the scenario in detail. Many years ago, JSR 305 proposed annotation types to help with bug detection. The famous ones are javax.annotation.nullable and javax.annotation.non-null. Guava supports them, despite the fact that JSR 305 to this day has not been finished. The javax.annotation package is actually owned by JSR 250, Common Annotations for the Java Platform. There's a module dedicated to JSR 250 called java.annotations.common. It exports the javax.annotation package. So guava.jar comes along on the class path expecting to find the nullable type. Thanks to JSR 305.jar, the unnamed module contains the javax.annotation package, but the module system doesn't notice this when the boot layer is set up. Instead, the unnamed module reads the javax.annotations.common module, which exports the true javax.annotation package, and there's no nullable type in that package. Guava gets a no-class-def found error. What's the solution for Guava users? One option is to lobby for JSR 250 to include nullable and non-null types in the official javax.annotation package. Another is to lobby for Guava to include nullable and non-null types in its own package. Notice that these are really governance issues, not technical issues, and that's a common thing we see when migrating to modules. Here's a similar scenario, but this time with a better outcome. For many years, JAX-P did not include the DOM element traversal API from the W3C. In concrete terms, JAX-P included the org.w3c.dom package, but not the interface element traversal in that package. The Apache Xerxes XML parser wanted to implement the DOM element traversal spec, so they included that interface in xerxes.jar. In JDK 9, when the w3c.dom package is exported by the Java XML module, so the same package in the unnamed module is ignored. Xerxes will get a no-class-def found error, just like Guava. This story has a happy ending. JAX-P agreed to include the DOM element traversal API in Java SE9. In concrete terms, we added the element traversal interface to the org.w3c.dom package in the java.xml module. It's as if JSR 250 agreed to add nullable and non-null to their javax.annotation package. Now, everyone who reads the java.xml module, including xerxes.jar and the unnamed module, can access the element traversal interface. The Xerxes version is ignored, but that's okay, because the interface in java.xml has all the right members. At this point, we've covered everything about the module graph and the class loaders that go into a layer. Let's see what we can do with a layer. As their name suggests, layers can be layered. When a graph of modules is resolved, it's actually resolved against a parent layer. Then, when the graph helps to create a new layer, the new layer picks up the parent. This allows a set of modules to have dangling references of a sort, requires clauses to modules that the module system will find in a parent layer. On the left, resolution has set up not only a reads edge between modules in one layer, but also a reads edge between modules in different layers. Constructing a tree of layers in this fashion is the job of a framework, such as an app server or a test harness. Layers give frameworks tremendous freedom to organize modules at runtime without upsetting the framework's traditional uses of class loaders. It's like the invoke dynamic instruction from Java SE7, a way for framework authors to interact with the VM to reify information about the overall shape of the program. If that sounds a bit abstract, let's look at one scenario where layers help out. Layers are how the module system supports multiple versions of a module. Here, an app server has created two layers, the Hadoop layer and the JavaScript layer. Each layer has two class loaders, and each layer has the boot layer as its parent, so its modules can read the java.base module. The Hadoop layer reifies a module graph with Guava version 11 and Jackson version 1, while the JavaScript layer reifies a module graph with Guava version 18 and Jackson version 2. Each module graph is well-formed and mapped to loaders in a sensible way, but the modules in the Hadoop layer are not aware of the modules in the JavaScript layer, and vice versa. But again, please note, this is all thanks to the app server creating the layers. The Java command line tool that you use to launch programs does not create layers like this. It simply maps modules on the module path to the application loader in the boot layer. Given the complexity of this topic, the takeaway is this. Just as modules wrap up coherent sets of packages and interact with the VM's accessibility mechanism, layers wrap up coherent sets of modules and interact with the class loader visibility mechanism. It will be up to framework authors to make use of layers in the next 20 years, just as they made use of class loaders in the past 20 years. So that was a deep dive into loaders and layers. Summary. Modules do a better job of encapsulation than class loaders, but class loaders are still necessary. After all, we have to have a way to load classes. Layers control the relationship between modules and class loaders. And finally, assuming class loaders respect the module graph, the system is safe by construction. There are never any cycles or split packages. Zooming out, here are the 3 key points. Modules are strongly encapsulated by the compiler, the virtual machine, and core reflection. Unnamed and automatic modules help with migration, and the resulting system is safe by construction. I'll say it again, there are never any cycles or split packages. In essence, the module system is a seatbelt. It's not a jetpack. There's a long road ahead. The module system is conceptually simple, but in JDK 9 it's associated with changes that probably won't break your code, but might break code upon which you depend. We've tried to support migration as far as possible, but it takes only one unmaintained library using a JDK internal type to prevent a migration to JDK 9. If that library can't migrate, then neither can anything on top of it. In this regard, modules are unusual. They suffer from a tragedy of the commons, whereas most big features like generics or lambdas let people opt in at their own pace without needing to wait for others. We've now come full circle. We started yesterday with a talk on prepare for JDK 9, and here at the end of Under the Hood, I'm talking about how to prepare for JDK 9. What can you do? Well, try JDK 9 with Jigsaw, as many of you have. Here's the URL for the download. You can run the JDAPS tool, which we've discussed in previous sessions, on your code and on class paths of your applications, discover uses of internal APIs, and eliminate them, as Dr. Deprecator might say, with extreme prejudice. And finally, you can subscribe to the Jigsaw dev list on OpenJDK to report problems and share solutions. I work for Oracle. Thank you very much. So we have 14 minutes left for questions. Alan has kindly offered to run the microphone around. So please raise your hand, or you could ask a question on Twitter by, why don't you just tweet at me? I'm Reinhold.
Okay, I just wanted to ask if you tested against JavaSys and other libraries that actually manipulate bytecode at runtime and inject classes into class loaders. And can you even create classes in other packages so you don't have access to the actual file when you load the class? It's an array of bytes, and it loads it into the class loader without any checks on split packages and that kind of stuff.
You want to answer this, Alan?
Okay, so most of these tools like JavaSys, they're based on Java-Lang instrument, and that has already been updated in the Jigsaw builds to work correctly with modules. There will be work that will have to be done, it's not in the builds yet, to be able to add some additional support that agents will need. But I would think that most of the agents that you have that are there now should actually work. Try them out. If you run into any problems, report it on the Jigsaw dev list.
Excuse me, the network is apparently down, so I'm switching.
Yeah. Thanks a lot. Could you please explain one thing? For instance, if you have some module with two packages, one is API and another one is SPI. In API, there is some interface IA, which is backed by some SPA impl, for instance. Will I be able from another model to somehow with static method of interface get this implementation up and running?
I'm sorry, that was a complex example.
Well, I mean, the simple thing, I have exported interface and hidden implementation. Is it possible to be used with module system?
Yes, of course.
Providers.
Yes.
Yes,
Sorry.
exactly.
Yes, you can have an implementation class. You put it in a package in your module that is not exported. The other code in your module can access it, but code outside of your module cannot, except perhaps through an interface.
Okay, then my question is, if I'm using reflection, will on runtime get the class, I will receive not the class of interface, but the class of implementation, right? Which is hidden.
Yes.
And thus, well, we end up with situation when I normally can call some public method of this service provider, but I cannot do so with reflection.
No, you can still do. Sorry, you can.
I think I can. Because, well, I will receive the class type of implementation, not the interface, but implementation is hidden.
That's true. And in that case, via reflection, you will not be able to invoke the method. If you were not using reflection and you invoked an otherwise accessible method via an interface implemented by that class, then that would work just fine. But from reflection, it will not work.
So is it normal situation then? I mean, you are breaking one of the, I think, very common approach in programming. We simply end up that we can.
Remy wants to
Remy
answer,
wants to answer
but
this
we also have limited time, so I'd rather not
I think we're getting
dwell
into
on any
circular
particular question.
Yes, it's a normal situation. It's exactly like if you have a class which is not public, which implement an interface. By reflection, it will not work.
Okay, thank you.
With our hand up first, I'll take this one.
Yeah. Hi. So we have Java class loaders since a very long time. So the next thing, obviously, would be, in my perspective, to have dynamic loading of modules. So I start a GRE that is, I don't know, a couple of megabytes, and then I say I want Java base to be downloaded from a repo or something, and then I want to kill something, and the virtual machine stays alive. And
Use OSGI.
Yeah, but
I mean, not for the platform modules themselves, but what you're asking for is something far more sophisticated, complex, and difficult to get right than what we're trying to do.
Do you plan to do it?
No.
Okay.
We actually did something somewhat like this a few years ago. If anybody here remember the Java kernel feature? That was an attempt to dynamically download the JDK in little bits and pieces as your program used them, and it was extremely difficult to make it work well.
I had a question about build systems. It seems like you give dependencies in the module system, but like Maven has also dependency management. Do you think you're going to need a whole new build system to really make this work?
Oh no, hopefully not. Our hope and expectation, and we've already had good conversations with a couple of the Maven committers, is that Maven will be enhanced. It doesn't need a rewrite or anything, but enhanced to support modules. That's one of the main reasons that we chose to stick with the jar file format, despite all its drawbacks. All the tools understand it. And if the difference between a jar and a true module is the presence of one more file in the zip format, that makes life a lot easier for the tools ecosystem to adopt. So no, we do not expect new build tools to be necessary. Doesn't mean you couldn't write one, but
like for automatic modules, you give the name of the jar file and that's the module name?
well, no, an automatic module is defined by taking its jar file and putting it on the module path.
Okay.
The name of the module is derived from the artifact name. And don't worry, if there are version numbers, we leave them out.
Okay.
That would be stupid to include them. Not getting many questions on Twitter, but that's okay.
Any other questions?
Any other questions in the room?
I think in one of the last sessions, I don't remember which one it was, you mentioned that resources are never exported. So that's kind of unexpected because, I mean, what you export are packages and not classes. And on the other hand, I can imagine that this is a problem for projects which have lots of mapping files for Hibernate or Spring configuration files or whatever. Can you explain the reasoning behind this decision?
Sure. So modules, as conceived, they're program components for the language and the virtual machine. If you look at the language in VM specs, there is no concept of resources. Resources are something at a higher level. They're defined essentially by class loaders. Via the reflection API, you can get at a module's resources. So if you've got code that relies on the ability to go poke into a module and read, meta-inf/hibernate.xml or whatever, that can still be done. But there's no notion in a module declaration of saying, export resource, foo/bar.txt or something like that. There were some nasty compatibility issues also around the way the class loaders handle resources, and so there are some slightly incompatible changes as code goes from outside of a module is migrated into a module. Some of the class loader get resource APIs will work differently, but they kind of have to in order for the overall design to be consistent.
Could you maybe shortly elaborate how the service lookup with provides and use works together with layers?
How does service lookup work with layers? Short answer is it's pretty much in the obvious way. You start in the layer you're in, and you look for service providers, and then you move up. So a provider in the layer in which you tried to load the service will override. Will appear first before a provider later on. Alan has worked on this. Maybe he wants to elaborate more.
Yeah, there's an update to the service loader API that actually has a load method that takes a layer. So it'll actually be able to, in the slide that Mark had, the layer of layers, it's quite obvious how it'll actually, how the lookup actually works and how you can iterate over service implementations that may be in multiple layers.
Okay, a couple questions on Twitter. Automatic modules read each other. This creates cyclic dependencies. Very good. Why is this not a problem? Well, it is a little bit of a problem, but it's worth accepting. It's worth accepting this in order to make migration easier. The cycles introduced by automatic modules are not introduced by the resolution algorithm. So the way automatic modules work is resolution happens first. We build a clean acyclic module graph. Then we looked around to see if there are any automatic modules on the module path, and then those things are added to the graph. And as you noticed in the diagram, there are plenty of cycles. So it is a little bit of a problem, but it's a problem worth having because automatic modules make migration so much easier. When a module exposes another module, it needs to export public the module. Well, no, it requires public the module. Isn't it possible to do this automatically at compile time? Well, you could do it automatically at compile time, but that's putting a pretty big burden on the compiler and could lead to some surprising results. But we are thinking about having the compiler give you warnings if you're compiling a module and it exports a package and a type in that package references a type that's in some other module, but your module does not require public that particular module, so that you're basically causing pain for your users. We're thinking of having a warning for that case. So at least the compiler would warn you. You could choose to ignore it, but the compiler would warn you.
Do you think that the OSGI world will evolve spectacularly, benefiting from the modules from the Java core?
Spectacularly? Who knows? So we obviously we talk to people who work on OSGI. Peter Kreens is in the expert group for the JSR. Our intent is to make OSGI interoperate, at least to some degree, with the Java platform module system, and it may prove out that OSGI itself can take advantage of some of the strong encapsulation benefits, the strong encapsulation mechanisms that we're baking into the virtual machine. But that's more for people who work on OSGI to work out. I think we've got time for one more question, as long as it's short. I don't even know where Ellen is.
How will you implement plugin mechanisms where you don't know the package at compile time and try to instantiate classes or invoke public or even private methods?
So I think what you're asking about is a framework type thing that loads things dynamically.
Yeah.
Layers are generally the right answer. So if you're implementing a plugin, for every plugin you load, you would create a layer for it, would have one class loader or maybe a few that would load your particular plugin and relate the plugin's modules to all the modules that you already have. Did I answer your question? I'm not sure.
I'm not sure exactly. No.
Okay. Well, the sign is telling me that time's up, so perhaps we can take it out in the hallway. Thank you very much.